So welcome back, geology students. We left off here on this slide, and I was trying to get it to work, and I've got it to work. This was, it's an animation that was created by the Earthquake Research Institute in Tokyo, and we were talking about how earthquakes generate these tsunami waves, and we were talking about predicting these, and they've actually have done that, and this is like an animation showing basically from blue to red. It's showing the water height of the tsunami. And there was a earthquake that happened in 1960, and I guess it was like the world's, or not the world, yeah, it was the largest recorded earthquake in the world. It was like a 9.5. And it killed like 1,655 people in southern Chile. And it created this tsunami that was unleashed in the Pacific, and it also that killed 61 people in Hawaii, Japan, and the Philippines. So this was created, to help predict. And if you know several things, if you know the distance and you know the velocity, and you know that, then you can calculate the time it's going to take for the wave to reach a certain location. And they did that here. This was actually done in Hawaii, the Department of Transportation. Basically, they use this to help use it as a prediction tool. And they, have right here where it emanated the star is where the tsunami was started out. And you can see these little kind of curved, little crests of the wave represent the time. So here's 3 hours, 6, 9, 12, 15, 18, and roughly 24 hours. So you can actually warn the people in Hawaii. For instance, it says here that the tsunami warning alarms sounded at like 6 a.m., giving the residents 5 hours to evacuate to higher ground. I think here is Hawaii over in here. But yeah, they can use this and calculate. Also, they have tide gauges in the ocean that also can record different parameters, and they use that to help them build a better model. But this is essentially it looks like it'll hit Asia, New Zealand, and Australia in 24 hours, which is roughly over in here's Australia. So yeah, so it's a good tool that they have. That they can calculate all this stuff with all the data that they collect. So here we'll watch a short, brief video of a tsunami wave in Japan. So I will kind of move this here and escape, and we will check this out. Let me copy and paste this, and then we'll move. Oh, actually, it's right here. So enjoy. This is just a little movie. So there's the wave out in the ocean, and it's not really the wave hasn't formed yet, so it isn't very tall, or in height wise it's not until it reaches the shore here. But this, I assume someone is either it's a drone or it's a helicopter for this footage. So when it does hit land, when it does hit the shore, it is pretty devastating. It'll take it's going to take a little bit to get there here. Oh, here it is. This is the cool part. So yeah, this is where it's reached the shore, and it just barrels through all these houses and knocks them down, and debris is everywhere. And if you saw that movie, there was a tsunami movie. I think it was in Indonesia, It was a good movie. You guys, I don't know what the name, remember the name of it is, but you can find some good tsunami movies. Wow, look at that wave just hit that house right there. Wow. That's a good view there too. Look at that. It's just like a slow viscous fluid. It looks like kind of just look, it's taking houses and garages and cars with it. Yeah, the energy that's behind this is it's crazy. Wow. It looks like it's going to get ponded here. Or maybe not, I don't know. Yeah, it's kind of getting clogged up there. So that's basically the kind of the movie there. Um, so now we're back. Let's see. So here's just a little. This is a kind of little side note. This is I guess a tablet, an ancient tablet that was placed on higher ground, and this is from Japan, and basically it just says here that the people should build on higher ground and shouldn't. If you build a house below this tablet, that it's bad luck basically, and there is some people that I believe in the article it says. It's basically was advice for advice. The dozen or so household of Anaishi heated their homes emerged unscathed from a disaster that flattened low-lying communities elsewhere and killed thousands along Japan's northeastern shore. So there were some Japanese people that didn't listen to this ancient tablet, and their houses were basically just destroyed. So just another. That's kind of just a more kind of just interest for this tablet. So here's a earthquake in Hawaii. It was like a 6.9, and it's just showing all these different colors. Show the magnitude. Red is obviously the 6.9, and all the greens are 3 to 3.9, and blues are 1 to 1.9. But down here is just a graph that's showing you the daily, a day by day, and the magnitude of the earthquake. And here is on May 5th, that's when the 6.9 magnitude earthquake occurred, and it occurred, looks like, in the ocean. But there was a Helena slump that caused an instability and a landslide to the ocean, and we'll talk more about submarine landslides as well. So here's the landslide that occurred. It was basically debris from enormous landslides off Oahu and Molokai, extended hundreds of kilometers, and it's showing you here basically this scarp. There was a bunch of rock here, and it basically just slumped into the ocean here, and it was basically a submarine landslide. And here's kind of more details of that. Here's Mauna Loa, and it was one of these large underwater landslides that it's called the Helena slide on one of these islands. And here's kind of a diagram showing you here's where the Helena slide is that occurred here. And what they did also, the Woods Hole Oceanographic Institute, what they did is they actually monitored the deformation or displacement of this landslide by placing these, they call them extensiometers. They can place them on the soil, and they can actually measure the displacement. And here's what that's showing. That here is these little the orange circles are GPS and seismometer, and the red ones must be the GPS buoy here. But it looks like the slide was moving at roughly 5 centimeters per year here, and it looks like they used GPS obviously for that. Oh, here is this is what the yellow diamonds represent the extensiometer with the pressure sensor. So they can actually, measure that and collect the data for that. So here's kind of just showing you the key. K is the Kilauea caldera. HF, there's your Helena faults. So remember what a fault is. It's basically a planar discontinuity. It's a crack in a rock in which the rock is going to slide. So here the movement was, in the direction of these orange arrows, and it roughly was 5 centimeters per year. So this was something that was triggered by an earthquake. So some of the safest and most dangerous buildings. Small wood frame houses, safest. Steel frame, obviously. Reinforced concrete. Unreinforced masonry. Adobe are the most dangerous, obviously, because those are made of clay, and they're good for regulating heat. However, they're not structurally sound. So this is an interesting map. It's showing basically the intensity and bedrock depths of San Francisco in 1906. And it's then showing, basically up here, it's showing basically the brown all the way down to this reddish color is the bedrock. And then this is basically mud, alluvium, and greater than 30 meters thick. And this is alluvium at less than 30 meters thick. So this is just, they're talking about this is just basically dirt here. And over here, down here, it's showing the distribution of, where the earthquake was weak and then strong all the way up to very violent. And basically it's just saying, where do you see the structures suffer the most in here? Where do you see them? So if you were to look at this, so here you're having alluvium. So this looks like very strong here. Where's this green? So it's weak here. So this is bedrock, roughly. This is bedrock. So you're getting where there's bedrock, it's very weak. So what does it say here? This increase, they pass from bedrock to water-saturated material. Structures there suffer as a result of this. So the yellow too is strong. And where is it? You're in alluvium here. So it's kind of a nice map showing kind of where your structures are suffering the most and what type of materials they're built on. So this little piece is violent right here. This is violent. Where's the brown? You got very violent down here, and that's on alluvium. So yeah, so it's on sediment or soil. And then here you've got weak, and this is on the bedrock. So actually you're better off on the bedrock. This is more bedrock here. And yeah, you're strong to weak in here. And your most violent is going to occur, obviously, in the muds along the shore. And then, so if you anchor to bedrock, obviously you're still going to have instabilities and, brittle type fracture, but it's not as bad as if you're on sediment. Obviously, the sediment's going to destabilize. If you have a lot of water pressure in the sediment, it's going to weaken. So rebar in the freeway. This is in California. It looks like this was just basically broken off and exposed this rebar. So earthquake magnitude. Typically, to measure the degree or strength of the earthquake, they're going to use this is the most typical, is the Richter magnitude scale. And this relates basically to the energy release. It's usually exponential. There's no upper or lower bounds. The largest quakes, about a magnitude of 8.7, and it's determined from the amplitude from a seismogram. So number 2, there's the seismic moment magnitude. So this is basically where a seismic